So for those of you just joining us, we want to find the area of the region bounded by all these things. There's a loud out there. So if I was doing this as a homework problem, like if I was a student and I was doing this as a homework problem, I would probably graph these on Desmos to see what they look like. And if it was more of a test situation, it's not really an option, we'd have to kind of graph them on our own. So we need to know what these things look like. I know that 2e to the x does like that. And it's got an intercept at 0, 2. 2 minus x squared is a downward opening parabola. It also goes to the point 0, 2. So it probably looks something like this. Um, 2x minus 1, so that's a straight line going up from left to right. It has a y-intercept of -1 and an x-intercept of 1/2. I would probably say the next point is the point x is 1, y is 1. So it does something like this. These probably intersect somewhere over here as well. These probably don't intersect. And then x equals 3, which is a vertical line somewhere over here. Sure. So, sorry. So that's what my region, well, that's what my graphs look like. This thing is kind of weird to see what the region is that we need to find the area of. So we have to be very, very, very careful. It's not that. It's not this. It's not that. It's not this. So here's the thing. If I say I want the area of the region bounded by these 4 graphs, then the region has to have each of those 4 graphs as one of the boundaries. And this region here has y equals 2e to the x, has x equals 3, has y equals 2x minus 1, and has y equals 2 minus x squared as its boundary. So you have to be extra careful when there's a lot of functions to figure out what your region actually is, because there's a lot of like other things that get enclosed, right? This area in red here, not what we want. That's the area bounded, or the region bounded just by y equals 2e to the x and y equals 2 minus x squared. Similarly, right, this region here, which I will color in blue, sure, why not? Right, this region here in blue, also not what I want, because it only has 3 of the functions as boundaries. And it has y equals 2x minus 1, it has y equals 2 minus x squared, and it has y equals 2e to the x, but it doesn't have x equals 3. So this region here is the boundary, is the region we want. Now, when we're finding the area of a region, right, we're just thinking about adding up a bunch of rectangles. So let me erase a little bit here. So the idea is, right, in this region, I'm going to add up rectangles. So to quote unquote add up the rectangles, that's where we do the integral. So the area of, well, so let's start to the left here. This rectangle I've drawn to the left. The area of that rectangle is the height times the width. The height is the top function minus the bottom function. So the area of that rectangle is going to be the height, which is going to be the top function minus the bottom function. So 2e to the x minus 2 minus x squared times the width, which is just dx. Right, so again, that's the height. That's the width. And then we're going to add up all the rectangles, meaning we're going to integrate. So we're going to add up. And now here's kind of an extra piece we haven't had to deal with really yet. we have to think about how far left and how far right. So the rectangles that have this height, where the top function is 2 e to the x and the bottom function is 2 minus x squared, definitely start at x equals 0, right? Those definitely intersect at x equals 0. You can set them equal to each other, but it's really easy to be like, oh yeah, if x is 0, y is 2, they intersect there. Now, how far right do they go? Well, the problem is right here, we have a change. If you move past this vertical line, it's going to start being that the top function is still 2 e to the x, but the bottom function now is 2x minus 1. So we have to figure out where these two functions, what this point is, where they intersect. We have to figure out where 2 minus x squared equals 2x minus 1. Now, here's the thing. We could totally solve this equation. We could also make a guess, though. What if we guess? So we know it's not 0. It's somewhere between 0 and 3. It's probably 1 or 2. If we guess 1, 2 minus 1 equals 2 times 1 minus 1. Oh, that works. So sometimes guessing a likely answer is not a bad way to go. It's certainly easier than bringing everything to the right and saying I've got x squared plus 2x minus 1 minus 2 is minus 3 equal to 0, and then factoring this as x plus 3 times x minus 1. You'll still get the answer x equal to 1. You'll also get the answer that's not important right now, which is x equal to negative 3, which is this point over here. But what I'm trying to point out is that if you want to just say, I think it might be easy, I'm going to guess a number that could be the answer. And if they're equal to each other, great, you're good to go. Okay, now we have to deal with this region here, right? So far we've only gone from 0 to 1. I know my picture's getting a little bit messy, I'm sorry. Now we need to go from 1 to 3. Well, that's easy. We know what the limits of integration are going to be. So I'm going to erase down here if you don't mind. The rest of this area is going to be, so again, the area of the rectangle is base times height. The base or the width is dx. The height is the top function minus the bottom function. And then we're adding all of them up from as far left as 1 to as far right as 3. So that's how you would set a problem up like this. The integration part, although it is not super hard, we're going to do it. But I just want to point out, right, the hard part of this problem is drawing the thing, which I would certainly encourage you to use Desmos to see where these things, what region you want. So like if I was doing this in Desmos, all my graphs would be different color, and I'd be like, okay, I need the region that has each color graph as one of the boundaries, at least. But the integral is not too bad. So actually calculating this, we would anti-differentiate 2e to the x and get 2e to the x. The antiderivative of minus 2 is minus 2x. The antiderivative of x squared is x cubed over 3 from 0 to 1. Plus, then we're going to do this one. Integral of 2e to the x is 2e to the x. Minus the integral of 2x is x squared. And the integral of minus 1 is the integral of 1, which is x. And we're going to integrate that from 1 to 3. Actually, we're going to evaluate that from 1 to 3. And then the rest is just terrible arithmetic. I mean, it's not even that terrible, right? So I feel like I shouldn't erase this yet. So I guess I'll write it over here. So we had, sorry, I know I just wrote on the same thing. 2e to the x minus 2x plus x over 3. From 0 to 1 plus 2e to the x minus x plus x from 1 to 3. So whenever we're evaluating these definite integrals, we're always plugging in the top first and then subtracting and plugging in the bottom. So plugging in 1, we're going to get 2e to the 1 minus 2 times 1 plus 1 cubed over 3 minus, this is a place where we have to be careful. Plugging in 0 doesn't mean everything is 0. We get minus 2e to the 0, which is just 2 times 1, which is 2, minus 0 plus 0. Plus, then we're going to do the same thing here. We're going to plug in 3, and we're going to get 2e cubed minus 3 squared plus 3. And you can put some bigger brackets around this. Minus, then we're going to plug in 1. We're going to get 2e to the 1 minus 1 plus 1. And then we would try to simplify this. I don't think we really need to do that, but we could do a little bit, I guess, right? I've got 2e minus 2 plus a third minus 2 plus 2e cubed minus 9 plus 3 minus 2e minus 1 plus 1 cancels. And then the 2e and the minus 2e cancels, and you're left with 2e cubed. And then you got to add up all the numbers. So minus 4 minus 9 is minus 13, plus 3 is minus 10, plus a third. You can make that more simple if you want to. I think we've done enough. Questions about any of this? Specifically, yeah. Yes, so we can definitely, I can definitely look at number 18, but more generally, we're going to talk about volumes in general. So I think, let me do one more area question, and then we'll start talking about volumes. So let's look at something like this. I'm going to look at one that's similar to number 11 on the homework, on Lee's homework. I'm going to change it up a little bit though. So let's say I want to find the area between f of x equal to x minus 2 to the, let's say, let's do x minus, let's change it up a little more. Let's say x minus 3 to the 5th, and g of x is x minus 3. And I want to find the area between these two curves. So, and I want to use horizontal rectangles, which seems like the wrong choice, but okay. So I'm going to draw both of these just so I can do the thing. So x minus 3 is just a straight line, right? And it has a y-intercept of negative 3 and x-intercept of 3. So that's what x minus 3 looks like. And here's the thing. I know that this graph will actually have the same intercepts. No, not the same x-intercept, not the same y-intercept. X minus 3 to the 5th is going to do something crazy. It's probably going to do something bonkers like this. Oh, that's why I have to do two intervals. Okay. Again, right, we can use Desmos to graph things if we don't know. Or we could just set them equal to each other to find the points of intersection. So if I set x minus 3 to the 5th equal to x minus 3, I know it's very tempting, but you don't want to divide both sides by x minus 3. Instead, what you want to do is you want to bring x minus 3 over to the left, have x minus 3 to the 5th minus x minus 3 equal to 0. You want to factor out x minus 3. But with x minus 3 to the times, x minus 3 to the 4th minus x minus 3. This seems kind of terrible. I'm not going to lie. I'm trying to look at this problem and see if I guess it's easier if it's x minus 2. Okay. Sorry, and that should be not x minus. Sorry, I factored this out. I should have a 1 here. Apologies. So I'm going to set this equal to 0, and I'm going to get x equal to 3. Setting this equal to 0 looks kind of terrible until we realize we can be smart about it. We can just say I'm going to set x minus 3 to the 4th minus 1 equal to 0, which is going to give me x minus 3 to the 4th equal to 1, which means x minus 3 could be plus or minus 1, which means x is going to be 3 plus or minus 1. So x is going to be 4 or 2. So here's the intersection point when x is 4 and y is going to be 1. And I've drawn this kind of, Now I feel like I've made an error somehow because, so I know what the error is. I've drawn my thing wrong. So I do this a little wrong, which is fine. This graph is a little more extreme than I thought it was. It does something more like this. Like that. It still intercepts the x-axis, the y-axis somewhere, but we've got something like this, and something like this. So this point here, that would be the point where x is equal to 3 minus 1, which is 2. And if x is 2, y is going to be -1. Okay, so that's what the region looks like. And again, my picture maybe not the best. Let me draw it again, just to make it look a little bit nice. So we've got intersection points at 3, 0, 2, -1, and 4, 1. One of our lines looks like that. The other one looks something like this. And this problem specifically asks us to do it in terms of dy, meaning we have to use horizontal rectangles. So what's the area of that rectangle? Well, it's going to be the length times the width. Or the length, yeah, no, length times the width. The width is just dy. The length, well, just like with a vertical rectangle where the length is the top minus the bottom, the length for a horizontal rectangle is the right minus the left. The problem is we have to solve for things in terms of y. So this line is y equals x minus 3, which becomes x equals y plus 3. And this line, or this curve, which was y equals x minus 3 to the 5th, if we solve for x minus 3 is the 5th root of y, x equals 3 plus the 5th root of y. So the length of that curve is the right function, which is the y equals x minus 3, the 5th function, except it's x equals 3 plus the 5th root of y, minus x equal to y plus 3. So for this region here, the area total would be, so that's the area of the rectangle, and the total area would be the integral from as low as those go, which is 0, to as high as those go, which was, well, let's see, I think it was the 0.1, right? X is 4, y is 1. And then it would be 3 plus, I would write it as y to the 1/5 minus y plus 3, which will simplify a little bit, right? You could definitely simplify this as the integral from 0 to 1 of y to the 1/5 minus y, because the 3's would cancel out. Okay, and then this region is going to be very similar. Sure. Except for this region here, what's the bigger and what's the smaller function has changed. The bigger function is the rightmost function, which is now going to be x equals y plus 3. And the smaller function is the leftmost function, which is now going to be x equals 3 plus the 5th root of y. So this region here, which goes from the point 2, -1 to the point 3, 0, that's going to be the integral from as low as -1 to as high as 0 of the right function, y plus 3, minus left function, 3 plus y to the 1/5. Which would simplify, the intent to simplify to just y minus y to the 1/5. So I'm going to fill up my water bottle because I totally forgot to. I'm getting thirsty. But let me know if you have any questions about that in just one moment.
The most precise.
Sorry about that. All right, so let's go ahead and talk about volumes. And have you guys talked about volume in class yet? You say yes or no? No, yes, Lee has. For Lee, I'm assuming, but I want to double check. Most of the time in 16B, we only talk about the disk and the washer method. Has there been any mention of the shell method? Okay, that's what I would generally assume. You guys let me know if you hear about the shell method. I don't think that's something we're going to cover in 16B, but sometimes some teachers get real kind of like I want to talk about all the things, so they cover that too. But I'm gonna assume for now that we're just gonna have the disk and the washer method. Okay. So here's the idea. So I want to find the let's actually start with this problem. So I don't know why I'm calling it number one, but I want to find the volume of the solid generated when revolving the region bounded by, in the first quadrant, bounded by, what have I got here? Y equals x cubed, y equals 0, and x equals 2 about the x-axis. Okay, now it's certainly not required that we draw a picture, but I do think it's helpful. So y equals x cubed looks, vaguely like this. X equals 2 is a vertical line, and y equals 0 is a horizontal line, the x-axis. And let's see, we have some points of intersection. Obviously, x cubed and the x-axis intersect at the origin. X equals 2 and y equals 0 intersect at the point x equals 2, y equals 0. And x equals 2 and y equals x cubed intersect at the point, well, if x is 2, y has to be 2 cubed. So those are all our points of intersection. And now the idea is we're going to revolve this thing around the x-axis. So I'm going to take this region and rotate it around the x-axis. So I'm going to get, let's see, where do I want to draw this? I think I want to draw it down here. And so I take that region and rotate it around the x-axis. I get a shape that kind of looks like that. To me, it kind of looks like, do you guys ever play Sorry? The little pieces in the Sorry game? It kind of looks like one of those Sorry pieces, but turned on inside. If you've ever played Sorry. If you haven't, you're missing out. It's a classic game. Anyway, so I want to find the volume of that. So here's what we're going to do. And this is, so the tactic we're taking here is very common, meaning just like when we found the area in a region by using a vertical rectangle or a vertical strip, as I will often call it, I'm going to do the same thing here. I'm going to take a vertical strip and then see what happens when I rotate it around the origin. When I rotate that strip around, not the origin, sorry, the x-axis. When I rotate that strip around the x-axis, what's going to happen is it's going to look like a little disc, right? That strip, which I'm going to draw in black here, and there's my little strip that's getting rotated around. And whoops, pen on the table. The volume of this disc is equal to the area of that circle, pi r squared, times the thickness of the disc or the width of the disc, which is dx. Now, the only thing we have to ask ourselves is what is the radius of this disk? Well, the radius of the disk is just how high that rectangle is. So the radius is just the function y equals x cubed in this particular example. So the volume of my disk is pi times x cubed squared times dx. Where we're thinking of, right, this rectangle is located at a distance of x from the origin. That's why the height is just whatever x cubed is, because it's the function height. All right, so now what we're going to do is we're going to add up all the disks, meaning the total volume is going to be the integral of this quantity from, well, the disks go as far left as 0. The disks go as far right as 2. Right? I've got like little disk over here, disk here, disk here. Right? I'm not drawing all of them because I can't, but that's the idea. We're just adding up all these disks, which is what we do, is how the way we add up all the things to integrate. And then we can integrate this and we can get what? That's x to the 6, so we get the integral from 0 to 2. We usually put the pi out front of x to the 6 dx. That's going to be pi times x to the 7th over 7 from 0 to 2. And then you're going to plug in 2, and you're going to get 2 to the 7th over 7 times pi. And 2 to the 7th is 128. So you get 128 pi over 7. But that's the very kind of basic idea, is that you're always going to be looking for some radius, and the volume of your disk is going to be pi times that radius squared. And you're going to add up all the disks. Or we could rotate around the y-axis. So, same region. But now we're rotating around the y-axis. And here's a really, really, really important thing to remember. If you're forced to use the disk or the washer method, the strip or the rectangle that you want to draw should always be perpendicular to your axis of rotation. So in the previous problem, my axis of rotation was the horizontal x-axis, or the line y equals 0, same thing. And my strip or rectangle that I drew was perpendicular to it, right? Horizontal axis, vertical rectangle. Here, my axis of rotation being vertical, I want my strip to be horizontal. But now, well, we're going to have a slightly different situation. When you rotate this thing around, it's going to look like, so normally when I rotate a thing, you don't have to draw the rotation. But when I rotate a thing, I typically draw like the outer boundary of this. So it's going to be like, you know, and then I want to draw like the inner stuff kind of, and then I'm going to reflect it over. There, there, there. And it's kind of, this is kind of a weird shape, right? So, it's kind of like a cylinder with kind of a bowl cut out of it. Sorry, just 1 second. I'm getting a message I need to respond to. Sorry, 1 sec. So that's the shape we're going to get. Now what's going to happen is when we rotate that strip around, we're going to get a shape that looks like well, it's no longer going to be a disc because we're missing the inner part here. So what we have is a washer instead. Sometimes it's hard to see it when it's drawn there. I can draw it down here as well. There's our not very well drawn washer. And the volume of a washer, well, it's the area of the washer, which is just a big circle minus a little circle. So it's area times the thickness or the width. So that's going to be, the area is going to be pi times the big radius squared minus pi times the little radius squared, right? Area of the big circle minus area of the little circle. And then the width is going to be dy, right? Because it's a horizontal strip and the thickness is a little change in y. So when you rotate this around, that's going to be my inner radius, and that's going to be my outer radius. So can anybody, and I know I didn't write the function anymore. This function was x equals 2. This was y equals x cubed. So can anybody tell me what the outer radius of this shape is going to be? It shouldn't be too terrible. I even said the answer just now. It shouldn't be too terrible. So fine, the outer radius is 2. The inner radius, on the other hand, is a little bit more complicated, right? So no matter where I draw this horizontal rectangle, the distance from the outer function to the axis of rotation is always 2. But when I draw my inner rectangle, if I draw my rectangle in a different spot, the inner radius certainly changes, right? Up here, the inner radius is super big. Down here, the inner radius is super small. So the inner radius depends on x and y. Specifically, the higher we go, the smaller, the larger the inner radius is. So I need to find my inner radius, but I need to write x as a function of y. So solving for x here, I get x equal to the cube root of y. And that's going to be my inner radius. So the area, or I should say the volume of my washer is pi times 2 squared minus the cube root of y squared times dy. Right? This washer has a large radius of 2 and a small radius of whatever the cube root of y is. Right? The higher you go, the bigger that is, the lower you go, the smaller that is. Okay, so then to find the total volume, we're going to integrate pi times 2 squared, which is 4, minus the cube root of y is y to the 1/3. And y to the 1/3 squared is y to the 2/3. From how low these go, which is they go as low as 0, to how high they go, which is they go as high as, well, this is the 0.28. So is the upper limit 2 or is it 8? Everybody could write a number. You could write 2 or 8, and you would have a 50-50 chance of getting it right. Yeah, it's 8. Because, right, we're thinking about how high and low the strips go. the strips go as low as y equals 0. They go as high as y equals 8. So when you're doing an integral, if it's in terms of y, limits of integration should be the y values of your boundary, right? The lowest y value is 0, the highest y value is 8. Where in the other previous problem, when we were doing the around the x-axis and our intervals in terms of x, we talked about how far left and how far right the strips could go, or the rectangle could go, which means our limits of integration were the leftmost x value and the rightmost x value. So basically just look at what variable you're integrating with respect to, and that's going to clue you in as to what kind of values you should be looking for your limits of integration. If it's a dx, you want the x values of your region. If it's a dy, you want the y values of your region. Meaning x values meaning the leftmost and the rightmost x value, 0 and 2. Dy meaning the bottommost and topmost y values of your region, 0 and 8. And then we can integrate this. You're going to get pi times 4y minus, the integral of y to the 2/3 is y to the 5/3 times 3/5 from 0 to 8. And then we plug in 8, we get pi times 4 times 8 is 32 minus 3/5 times 8 to the 5/3. Let's just write 8 to the 5/3. Minus, and when you plug in 0, you get 4 times 0 minus 3/5 times 0. Okay, so we end up with pi times, so check this out for a second. 32 minus 3/5 of 8 to the 5/3, 8 to the 1/3 is 2, 2 to the 5th is 32. Now, instead of doing something silly like getting a common denominator of this, look what I've got. I've got 32 minus 3/5 of 32. If I have a whole thing, 32 in this case, and I subtract off 3/5 of it, I'm left with 2/5 of it. So you could just say this is pi times 2/5 of 32. Or if you don't like the words I just said, you could factor out a 32 and say, oh, this is pi times 32 times 1 minus 3/5. And then you can say you've got 64 pi over 5. So depending on the axis of rotation, you're going to want to use a different kind of thing. If you're going around the y-axis, you're using dy. If you're going around the x-axis, you're using dx. Or as I like to say, your rectangular strip should always be perpendicular to your axis of rotation. Also, something that you might want to be like, how do you know if you want to use the disk or the washer method? There's a really easy way to tell. If your region happens to be bounded by the axis of rotation. So this region had the x-axis as one of its boundaries, and we rotated around the x-axis. If you are rotating around one of your boundaries, you're using the disk method because there's nothing missing, right? Your axis, your region is flush with the axis of rotation. So there's no inner circle you have to subtract out. Whereas here, our region, the y-axis was not one of the boundaries. So when you rotate this around the y-axis, there's all this stuff missing. We have to subtract out that volume. So that's why for this one, we had to use the washer method, where it's pi times the big radius squared minus pi times the little radius squared times the thickness. And in this one, we got to use the disk method, which is just pi times the radius squared times d, whatever, dx in this case. Okay, let's do some more examples. So sometimes, let's stick with this. Let's stick with this example for just a little bit longer. Sometimes people are going to ask you to rotate around different axes. So let's say we have the same region. But now I want to rotate, so same region, I'm draw it again. But now I want to rotate it around the line, say, x equal to -1, for example. Sorry, I meant to say y equals -1. Brain. Now that we can do x as well. So we do it around y equals -1. So now here's my axis of rotation. Here's my region. So let me ask everybody, based on what I just said about the disk and washer method and the axis having to be one of the boundaries, are we going to need to use the disk method here or the washer method here? You write a D or a W. D for disk, W for washer. What are we using? Like some more responses. Is anybody there? A few people are messaging me privately, which I appreciate. Yes, people are saying the right things. I would like 2 more people to tell me what method they think I should use before we do it. 2 more. Everyone's like, no, James, it's too early. I don't want to say anything. Really, nobody else wants to tell me what method to use? Okay, so it's definitely going to be the washer method. And the reason why is because, again, the region, the axis of rotation is not one of my boundaries, right? If the axis of rotation is one of the boundaries, then that's totally the disk method. But since this region is here and it's totally removed from my axis of rotation, we're going to have an inner thing that we have to subtract out, right? If we revolve this around that line, it's going to look like this. I shouldn't have drawn that. So it's going to look like that. It's going to be, I don't know how to call it, right? It looks kind of like, I don't know, let's maybe like, no, I don't have a good way to say, I don't have a good interpretation of what this looks like, but we can find the volume of it certainly. So if we look at, say, our vertical strip, when we rotate it around, it's going to be missing the whole inner circle there. So the volume of our washer, as usual, is pi times the big radius squared minus pi times the little radius squared, all times d whatever, dx in this case. What's my large radius? My large radius is the function. Okay, so here's where things are a little bit different. So the large radius isn't just y equals x cubed. It's the distance from your outer function to your axis of rotation. So in the previous problem, when I was going around the x-axis, which is y equals 0, my radius was just x cubed, but it was really x cubed minus 0. It was the difference between the function and the axis of rotation. Now, since my axis of rotation is y equals -1, the outer radius, well, this distance here is x cubed. This distance here is x cubed plus another 1, or as I would actually encourage you to think of it, it's x cubed minus -1. Hope you guys can kind of see that. And my inner radius is 0 minus -1. Which is just 1. So setting this one up, and we're not going to calculate this, we're just going to set it up here. You're going to get the total volume is going to be the integral. As far left is 0, as far right is 2. of pi times the big radius squared, which is x cubed minus 1 squared, minus the little radius squared, which is 1 squared. That would be the volume, how you set up the volume of this. Which wouldn't be too complicated. Yeah, so someone asked me a really good question. Can you always use the washer method while the disk method is only if the area is bounded by the axis you're rotating it on, or when there's nothing missing? Yes, essentially. So technically, right, you could have used the washer method here. It's just if you use the washer method here when we're rotating around the x-axis, the inner radius you're subtracting, like if you did pi times the big radius squared minus pi times the little radius squared, the inner radius is 0, so there's nothing to subtract off. So technically the disk method is the washer method. It's just the washer method when you have an inner radius of 0. Whereas right, this one here, there is an inner radius of 1 that we have to subtract off. Let's look at it. Let's look at another example. Let's finish this one off by looking at this region revolved around the line x equal to 2. So I'm going to ask everybody again, and I want at least 4 responses. If I revolve around the line x equals 2, do I need to use the disk method or the washer method? Chat it up, privately or not. I want to know. What do you guys think? Disk or washer? I've got some disks, I've got some washers. So I should say, technically you've used the washer because your inner radius could be 0. But the more appropriate answer is that it's actually the disk method. And the reason it's the disk method is because I said I was going to wait for 4, but I only got 4. Oh no, I got 4. Yeah. The reason it's the disk method is because the axis of rotation is one of the boundaries, right? This region is bounded by y equals 0, x equals 2, and y equals x cubed. And we're revolving around the line x equals 2, which is literally one of the boundaries I just said. So, right, if the boundary is the axis of rotation, or if the axis of rotation is one of the boundaries, that means disk method. And the reason why, again, is right, if I rotate this around the line x equals 2, right, I'm just going to take this region and flip it over. And there's nothing, right, there's no blank space that I'm missing. I often say that the region here is flush with the axis of rotation, meaning it sits on it. And if it's flush with it, right, there's no space to kind of be missing something. Whereas again, in this previous one, right, this region was not sitting flush with this axis of rotation. It was completely removed from it. So bring it something like this. It's gonna look like, again, I've kind of got that sorry piece shape, or as someone else has said before in the past, it looks kind of like a Hershey's Kiss. And right here is our strip here is just getting rotated around. Right, that's what's happening with our little. Right, that horizontal strip is being rotated around to make a disk. So I always like to do it this way. I like to think first of just what the volume of the disk is. Well, the volume of the disk is the area of the circle times the thickness of the disk, which is dy. Okay, and then we need to find the radius. So let me ask you guys, what's the radius of this disk? Oh, good question. Well, sorry, it's loud outside. The radius of this is just the length of this strip. And the length of that strip is going to be the right function minus the left function. So it's going to be the right function, which is x equals 2 minus the left function, which is, I don't want to write y equals x cubed. I want to write x equals the cube root of y. I know I've written this kind of weirdly, right? X equals 2 minus x equals y to the 1/3. What I'm really saying is here, I'm subduing 2 minus y to the 1/3. Right? X is a function of y minus x is a function of y. So that's my radius, or your length of your strip. That is what's going in there. So when you go around a different axis of rotation, your radius is going to change. So the volume of my disk is pi times 2 minus y to the 1/3 quantity squared dy. And then the total volume would be the integral of that, pi times 2 minus y to the 1/3 squared dy. And it would go as low as y equals 0 to as high as y equals 8. Questions about this one? Let me screen capture the people in the class. Okay. I'm going to do one similar, but maybe not exactly the same, to problem 18 from the homework. Yeah, well, maybe not. Yeah, we'll get there. Let's look at something like this. Let's say I want to find, so again, volume of region formed by revolving the, volume, it's not volume of the region, right? Volume of the solid, right? Even though it's always like, so volume of the solid formed by revolving the region bounded by y equal to the square root of x and y equal to, sure, let's do 1/3 x around each axis. Okay, so let's draw the region. We've got y equal to the square root of x, and then we've got y equal to 1/3 x, which definitely is below it like that. If you're not sure which one's on top, which one's on the bottom, you can find the points of intersection by setting 1/3 x equal to the square root of x. If I was going to solve this, I'd probably multiply both sides by 3 and then square both sides. So x squared equals 9x, x squared minus 9x equals 0, x times x minus 9 equals 0, x equals 0, x equals 9. So those are the points of intersection where x is 0 and y is 0, or where x is 9 and y is 3. And if you want to know which one's lower, you can pick any point between 0 and 9, like 1, and plug it in. If you plug in 1 here, you get y equal to 1. If you plug in 1 here, you get y equal to 1/3. So this is definitely the lower function. So now we want to rotate this around the x-axis. So let's see. I think we're using the washer method because our region doesn't have the axis of rotation as one of its boundaries. Right? The only boundaries of this region are y equals 1/3 x and y equals the square root of x. So I'm going to take this strip or this rectangle and rotate it around. And when I rotate it around, right, we get a washer. Right, there's our washer. And the volume of our washer is, as it always is, pi times the big radius squared minus pi times the little radius squared times the thickness. Okay, In this case, the big radius is the function that's further away from the axis. So it's going to be pi times the square root of x squared. And I factored out the pi because we usually factor out the pi. And then the inner radius is going to be the closer function, which is going to be 1/3 x. So if we wanted to write the integral for the total volume, we would be doing the integral from as far left as 0 to as far right as 9 of this thing here. So pi times the square root of x squared minus 1/3 x squared dx. And then we can calculate it, right? So again, the setup is usually the harder part. It's going to be, the integration part is not super, well, the integration part can often be kind of messy with the numbers, but as far as actually doing it, it's not usually terrible. Sorry, 0 to 9, square root of x squared is x, 1/3 x squared is 1/9 x squared. And then we integrate, we get x squared over 2 minus 1/9 x cubed over 3. I said over 2, but I wrote a 9. And then you plug in 9, and you get pi times 81 over 2. And 9 cubed divided by 9 is 9 squared, which is 81 over 3. And this would simplify to something. I think it's simplified to like pi times 81 over 6, which is 27 pi over 2. But again, this last part, like getting to this step here is really what matters. After that, the rest is just kind of like, okay, there's some stuff to calculate. And yes, I know sometimes you have to do that on the homework, but I want to put like on the exam, if you got to here, depending on your teacher, if you got to here, you should get most of the credit for doing the problem, in my opinion, anyway. Let's see what happens if we go around the y-axis. Actually, let's make it more interesting. So let's set up the integral for going around the line x equals 9. Yeah. We'll eschew the y-axis and we'll go straight to x equals 9. So here's our region again. And right, this is y equals the square root of x, 1/3 x. If I say y equal to 9, I'm going to say x equal to 9. So we're rotating around the line x equal to 9. So we have to use a horizontal strip. We're definitely going to be using the washer method because again, you rotate this strip around the axis. You've got a washer. And here is my, sorry, that's a terrible. There's my larger radius. There's my smaller radius. So using the washer method, right? The volume is the integral of pi times the big radius squared minus the little radius squared. dy in this case. And again, this was the point 0, 0. This is the point 9, 3. So let me ask, what's my large radius? What is this distance here? Okay, it's like, it's something minus something else. I suppose it might help if you wrote the function in terms of x as a function of y. So this is going to become x equal to y squared, and this is going to become x equal to 3y. My outer function, the one that's, so I should say, the function that's further from the axis of rotation in this, for this axis is x equals y squared. So the larger radius is going to be the difference between them. It's going to be 9 minus x equals y squared. That's my larger radius. Minus my smaller radius is going to be this distance, which is 9 minus the closer function, which is 9 minus 3y squared. And the y values go as low as 0 and as high as 3. And you can pick a number between 0 and 3, like 1, and see that, oh yeah, this radius really is larger than that radius. If y is 1, this is 9 minus 1, which is 8. If y is 1, this is 9 minus 3, which is 6. This is the bigger radius from 0 to 3. Okay. So let's look at something similar to problem 18 somebody asked me about. See, where'd you go, problem 18? Okay. This one does want us to actually find the volume. So let's say I want to find the volume of the solid. So volume of the solid formed by rotating region bounded by y equal to x squared and y equal to, sure, let's make it, I'm gonna make it a little bit different, 14x minus x squared. Numbers are probably gonna be terrible, that's life, about the x-axis. Okay, there's a really easy way to graph things specifically like this. Y equals x squared, we know how to graph that. It's the usual problem. And 14x minus x squared, if you, that's also a problem. It's a downward opening. If you set if you set y equal to 0, so if you set the whole thing equal to 0, 14x minus x squared equal to 0, you can factor out an x, and you get x equal to 0 and x equal to 14. So my intercepts are going to be x equal to 0, and somewhere over here, x equal to 14. And then halfway between, which is at 7, you'll have like the vertex. So somewhere at 7, you'll have like its highest point. I'll do something like this. So we're looking for this to be our region. The graphs clearly intersect at 0, 0. The graphs also intersect somewhere else. So we need to figure out where they intersect. So we're going to set this equal to that. So if we set 14x minus x squared equal to x squared, I would probably bring that over. So I get 14x minus 2x squared equal to 0. Factor out a 2x, and you're left with 7 minus x. So you get x equal to 0 and x equal to 7. So I've probably drawn this slightly incorrectly in that the point of intersection is actually at the vertex of this other graph. That's fine. It doesn't need to look perfect. But if you really wanted to, you could change it so it looked more like what you actually have. So it looks like that instead. Again, not a big deal if your picture is a little bit not correct. Okay, so now we want to rotate this around. We want to find the volume of the thing rotated around the x-axis. Okay, so once again, volume, it's going to be a washer because our region doesn't have the axis of rotation is one of the boundaries. So it's going to be the integral of pi times your large radius squared minus pi times your small radius squared times dx, right? Because we would use a vertical strip that's perpendicular to the axis of rotation to go around the x-axis. All right. And we know our limits of integration too, right? We know our strips are going to go as far left as 0 and as far right as 7. So the only thing left to do is to figure out which function is bigger. Now let's say we hadn't drawn it. let's say, in fact, yeah, I'm going to erase my picture. We didn't draw it, but we figured out where they intersected, which I just erased, right? And we set 14x minus x squared equal to x squared, and we ended up getting x equal to 0 and x equal to 7. And now I want to figure out, okay, which one's the bigger one, which one's the smaller one. So I just have to figure out between 0 and 7, which one is further from the axis of rotation. In this case, the axis of rotation being x equal to 0, so figure out which one has the bigger value. So pick any number between 0 and 7. I'm going to pick 3. Okay, if I plug in 3, this one's going to give me y equal to 9. This one's going to give me y equal to 14 times 3 is 42, minus 9 is 33. This one's clearly bigger. So the larger radius is going to be the 14x minus x squared. The smaller radius is going to be the x squared. So setting this one up, or finishing the setup, I should say. And you can do this if you're rotating around a specific axis, and the functions only intersect each other 2 places. You'd be like, oh, they intersect twice, and in between, one's always bigger, one's always smaller. It's a little bit, so someone asked me a very good question. Can you use the same method even when the axis of rotation isn't x equals 0 or y equals 0, but like when it was x equals 2 or y equals -1? It's a little dicier. I'll show you in a second after we finish this problem. So if I was going to do this, I'd have the integral from 0 to 7, factor out the pi, 14x minus x squared minus x squared, which is going to be not very nice, right? You're going to have pi integral from 0 to 7. You do want to multiply this out. 14 squared is 196. You're going to get 196 x squared minus 14 times 2 is 28 x cubed plus x to the 4th minus x to the 4th. So one nice thing happens, the x to the 4ths cancel. So then you're going to get pi, integrate this, you're going to get 196 over times x cubed over 3 minus 28 times x to the 4th over 4, which will be 7 x to the 4th from 0 to 7. And then you'll plug in the 7, you'll get some terrible number. But I think that question was asked is worth looking at. So what if instead they told us, okay, I want to take this same region bounded by y equals x squared and y equals 14x minus x squared. And I want to go around, I'm going to try y equals -2 and y equals, that's a kind of a big number, 50. Here's the thing, right? Because the reason that kind of big number is because your axis of rotation shouldn't cut through your region. And this region, which I have erased, goes pretty high. It goes as high as 49. So here's the thing, right? So we know that these intersect, right? These intersect at 0 and 7. All right. So then I want to know, yeah, it's kind of challenging to do it when you don't have the graph, right? If I want to know which one's further from my axis of rotation. So my big radius, well, I guess I can still, and my little radius, I can still try plugging in like x equal to, let's do 1 this time, which is between 0 and 7. If x equals 1, this one's going to be 1, and this one's going to be 14 minus 1, which is 13. But then you have to think about not just which one's bigger, but which one has the bigger difference between it and the axis of rotation. So around y equals -2, 13 minus -2 is 15. 1 minus -2 is 3. This is still the bigger one. So if I was going around y equals -2, my large radius would be the bigger function minus -2. The small radius would be the closer function minus -2. And my integral for around y equals -2 would be pi, still the integral from 0 to 7, big radius squared, which now has an additional minus minus 2, minus the little radius squared. On the other hand, if you're going around y equals 50, you have to look at the difference. So from 1 to 50, the difference is 49. From 13 to 50, the difference is 37. So now this is the bigger one. So for 50, my outer radius would be, and it has to be 50 minus this because 50 is the bigger thing. My outer radius would be 50 minus x squared. My inner radius would be 50 minus 14x minus x squared. So then my integral for this volume would be pi integral from 0 to 7, outer radius squared minus inner radius squared. So the answer to the question, can you do these without drawing the region? Yeah. Should you? Probably not. I think it's, to me, it is easier to tackle this sort of problem if you actually draw it.